Hello, my name is Mayday, and today we're going to be talking about my approach to encoded parallel restocking. So let's start with an example. Let's say you have a quad bulk haul. So you have displays here, 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 and here. So 4 per slice, 1 per quarter slice. And let's say these chests empty, and you want to restock them from your external bulk. Um, Now you could just restock down this line, move on to this one, and this one, and so on. Or you could restock this one, this one, this one, this one, all in parallel at the same time, effectively dividing your restocking time by 4. So in theory, this would be really nice. So from our encoded bulk, we'd send items to each of these quarter slices at the same time, which, we can make a quad bulk that's capable of that. Um, yeah, it sounds pretty nice, right? So it's a little involved, however. So first I'm going to quickly reiterate how passive restock works. And so this means that the chests in a display hall restock without any input from the player. So the way this works, a slice is emptied, the chest is emptied, and a comparator readout tells the control logic that there's an empty slice. We make a list of all the empty slices. In a previous video, I've explained this in more detail. We unlock the first empty slice, we restock it, we lock it, and we move on to the next. Once we're done with the list, we reset the system and we wait for the next empty chest. Restocking is a bit more in depth, so we're going to be restocking from an external bulk. We're going to send the code from the empty slice to unlock one of the slices in the bulk. We're going to take out items, we're going to set them to halt, and then we're going to lock the bulk slice. Pretty simple. This concept was developed by Optic Nerve. Yeah. So what goes into parallel restocking? Let's say we want to do this in parallel. Well, first we need an encoded bulk that is compatible with this. This one here is mostly the control wiring in the demo that I've posted is a little different. And I'll go into that a little bit. So there's some requirements to your external bulk. First, the bulk has to handle multiple requests at the same time. Obviously, if you're going to do things in parallel, you need to do many things at the same time. And with this, there's some timing concerns. We cannot send all the requests at the same time because we have a single input serial binary data line here. So, we can't clog that and send 2 signals on top of one another, for instance. I mean, it won't won't unlock the right size. Second, we have some item type concerns. The way this book is set up, we go by segment. So each of these 1, 2, 3, 4, 5, 6, 7, 8 segments can operate in parallel. And that means that we can't request an item from this, we can't request 2 items from the same segment at the same time. Right, we can't request an item from this segment and then request another one over here and reliably separate the 2 item types coming out of the bulk from the output dropper line. And so these requirements mean that we need per segment inputs and outputs. That means for each of these 8 segments, we need separate inputs and outputs aside from the data line. The first thing we need is an output, which is the ready, which basically just means that all the slices in the segment are locked. We need an input, which is the output trigger, meaning we trigger the dropper line in order to output items from that segment, from whichever slice is unlocked. And lastly, we need a locking trigger to come into the segment and lock all the slices. So there's a couple components I'm going to be going over that are involved in my implementation of parallel restocking. The first is the priority queue, shown here. And this particular implementation was shown to me by Obi. It's pretty nice. Um, Essentially, it is a bunch of latches. right? We have a latch here, a latch here, right? 7 latches for the inputs, one for if it's ready. Um, right, so for inputs, we have the requests, these latches, the ready, this latch, and then the enable is this redstone line. And note it's on low. So when this redstone line is off, the priority queue is enabled. Outputs we have in the back here, rail lines. And these are going to be for requests granted. So how this works, right? A request comes in via one of these observers, the latch goes down, the redstone block goes down, powering the repeater into the comparator. If this latch is down, sorry, this one behind with the no block and observer and the normal piston. You'll see the redstone line here. The redstone block will also power that, go through, and it'll send a pulse through these comparators, which trigger the redstone lamps, and it's synced with this repeater line down here. And back here, you can kind of see it. If those line up correctly, the comparator will turn on, and reset the latch for the request. And the observer will send a pulse through this redstone line, or sorry, this rail line here, which will go to whatever component is attached to each one of these inputs. It's important to note this is a priority queue. So if we, for instance, have this piston and this piston have extended, so these 2 latches are down, this request will always be granted first, just because of the nature of how the comparator line is directional. Next, we have a register. Here's the register. Again, this concept was shown to me by Obi. Here's a picture of each slice. I've modified it slightly to work for my needs. Yeah, this is essentially a bunch of latches. These controlled by a dropper latch here. Everything is latches. For inputs, which are these rail lines, we have the bit inputs, and then here the dust and the repeater, we have another input, which is the enable signal. And again, this is on low, so when this is off, the system is enabled. Outputs are bits. Yeah, we can also send these in series. And so the way this works is your input bit comes in, observer triggers, quasis the piston, which shoots the observer up. This observer here picks up that we've gotten an input, sends it to the control logic over here with some delay, switches over the dropper latch, depowers the torch under the piston here. Since this is a falling edge and we've inverted it from a rising edge, the observer goes down and triggers this top rail line here, which just releases all the bits through the trapdoor in the observer here. We're going to combine these two for one component. This is the register priority queue combo. And this is literally just a register on top of a priority queue. And what we're trying to do here is make a queue, which is essentially a priority queue, but we do not have any priority to the requests. And so this allows for some sort of quasi-queue behavior, which is what we want. And this will handle requests to send data to the external bulk. So the way this works is we have the register, inputs come into the register. If the priority queue is empty, we're going to send those bits in the register through to the request inputs on the priority queue. And at that time, the priority queue will be full. So we're going to de-enable the register. So any new inputs will just be stored until the priority queue is empty. We're going to go through the priority queue, grant each access request to send data through the single serial line over to the external bulk. Once the data has been sent, we just increment the queue, the priority queue, move on to the next request, and so on and so forth until the priority queue is empty, and then we can load in the new requests. This comes with some timing issues, unfortunately. Requests could be lost if they're sent while the register is releasing the bits. Right, so if this observer is up, right, this has previously received an input, And at the same time as we trigger this observer here and the piston's extending, wait for 3 game ticks, it'll be extended. This one can't extend. So in that window, if we trigger this observer through inputting a request, that request will be lost. So you have to worry about that. But in my demo implementation, this hasn't come up yet, just because the system is quite slow. Next, I'm going to go into a little bit of a overview on how I've actually implemented the parallel passive restocking. So as before, this starts with an empty slice from, for example, your quad bulk. And this is going to go into a per segment bulk segment access priority queue. Now remember there's 8 segments to the bulk, and this is happening for each of them. So each of them have a dedicated bulk segment access priority queue. And this is similar to what you'd see in a non-parallel system, but you just have one of these bulk access priority queues. So if access is granted, we're going to go through the whole the whole passive restocking workflow. We're going to increment the list, we're going to make it, whatever. The list is done. We're going to increment the queue. We're going to say, your brewer, your furnace array, your player call, whatever, can access this segment of bulk now. As we increment the list and go through the passive restocking flow, we're going to load the code into a register coming out of each quarter slice of your quad bulk. And a code being present is going to prevent granting new access requests, because we don't want to overwrite what's in the register already, or kind of do bitwise OR on 2 requests. Right? That's not going to get us the items we want from the external bulk. A code being in the register will create a request for data line access. So this is requesting to send the code from the register to the bulk through that single serial binary line. This is where the register priority queue combo comes in. So once that's granted, we're going to send the code to the bulk. From the bulk, we'll get a segment unlocked signal. So that's just confirming that our code has been sent. From this, we'll increment the queue on the data line access queue. So move on to the next request, or just make sure it's ready for the next request to come in. Again, from this segment unlock signal, we're going to start outputting items. So we're going to pulse the output dropper line. We have a counter hooked up to that. Once we're done, we're going to lock the segment. So we have per segment locking, so we can lock just that segment, but allow whatever else is happening in the bulk to keep going on. After we lock the segment, we'll get a confirmation signal. We start a little timer, just making sure all the items get there, or we're just accepting that bulk has no items to send back. And then we're going to go back and increment the bulk segment access priority queue. And so that allows for, whatever other components you have that are requesting items from the same segment of bulk to start working again, and their requests to be granted. And so basically we just go through all the items, all the slices that are empty in the quad bulk. And using this method, we can restock up to 8x hopper speed in parallel, which is great. And this number depends on how many segments you have in your external bulk. Here we have 8. You could make this smaller in terms of the segment length and give yourself more segments. But I thought this was a good balance for the demo. And it also fit nicely into the length of my halls. Anyways, this is the end. If you have any questions, please let me know through Discord or whatever. And if you'd like a demo, just seeing this in action, I have one posted on my channel as well. Thank you.